Yeah, so let's wait for a few more minutes. Let's see how many joins. Then we'll start. Yeah, so let's begin. Hello everyone, my name is Sujay Mukherjee and I'll be taking this live session for NPTEL course on operating system fundamentals. We'll be discussing some problems related to this work's course, as well as we'll do a small recap of what has been taught in this week. So let's begin this week's one. So in the final week, the week 12. So let's do a brief recap of what we studied last week. Uh, so previously, uh, previously we came across page faults, right? And virtual memory concept, page faults, virtual memory, and how to like what is thrashing, etc. So what we saw, what the page fault was that. So what happens when a program starts? When a process starts. So when a process starts, what happens is, instead of capturing all the instead of uh, instead of loading all the pages at the same time, what we do is we start with a small set of pages which are required for running the process for initially. So we begin with that, and after that, what happens, as and when required, we pick up those pages from the secondary memory. So basically, but from virtual memory. So as we know, virtual memory is basically your uh, virtual memory is basically your main memory plus secondary memory, right? So what happens is, what happens is, when you have a set of pages, so your process starts with, let's say, your process P1. It starts with, let's say, uh, it has a total of 40 pages. So it starts with, let's say, so all these 40 pages are stored in your virtual memory. So all these things are stored in your virtual memory. So what happens when so this process P1 has a total of 40 pages. Let's say it starts with 8 pages. So we saw that uh, if if the OS requires new pages to run the process, what it does is creates a page fault. And as a result of solving the page fault, what we do is we bring the page from your secondary memory to the main memory and the page table and all. So we saw that there are many procedures of how to do this page scheduling and all. Like so when you are being solving a page fault, it comes one which so the process after a page fault happens is that what? So there are two things to be done. You need to evict one page from main memory, load the required page from virtual memory, right? Now, so the question arises, which page to uh, evict? So we saw that there are many algorithms to so we saw there are many algorithms to do this. So like there was your recently used least recently used first come first serve FCFS, first in first out, and then there is your round like circular the ring schedule. So these are the algorithms which we discussed last week. So in relation to this concept of page fault, like which one to evict and which one not to evict, then we also studied the concept of thrashing. So what was thrashing? Thrashing was basically are you are always evicting a so after every run you encounter a page fault. So after, let's say, in this case you have 40 total pages of 40 and 8 are loaded into it. So after, let's say, 8 seconds you require a new page. You bring your ninth page back, but after that you again need a new page. So the OS is continuously evicting a page from your main memory and loading a page from your memory. So basically your OS is spending a lot of time in this process of page fault, serving page fault, and in the process of serving page fault, where you need to you need to evict one page and bring one page. So this process was called thrashing. So as a result, as the name suggests, thrashing is not good. So thrashing will considerably slow down the process uh, of your performance of the CPU. So there are many views on how to stop thrashing and all. So one can be just increasing the page size, number of pages that are allowed. Those kind of tricks has previously been targeted. So we'll now start discussing what we this week's topics for which were covered. So this was just a brief recap what happened last week. So let's start this week's one. So we are discussing this working sets and page faults. So working sets. So there is a direct relationship of the working sets of a process and its page fault. So working set is basically the set of processes, set of pages with which a process is initially run. So there is a direct relationship between the working set of a process and its page fault rate. So working set changes over time. Working set changes over time. So peaks and there are peaks and values over time. So as you can see, so there is a so as you can see there is a initial peak here. Uh, So there is an initial peak here, and then there is followed by a time of where there are no page fault appearing. So that is a common observation that has been found uh, in how page faults happen in your normal system and all. So if you have any doubt, anytime you can ask. I see people have joined it. So one more thing about this page fault rate is you see there is a continuous set like these are the set once they get loaded the time over time there is less chances of page fault. So that's a common working phenomena that has been shown previously observed previously. So we will discuss some other things like pre-paging, page size, TLB, and niche, etc. So let's start with pre-paging. So pre-paging is basically used to reduce the number of responses. So as well as discussing thrashing. So this is one big step to counter thrashing. Yeah. So this is a big step to control thrashing. So pre-paging is used to reduce it. So pre-page all or some of the pages the process a process need while before they are referenced. But if the pre-pages are unused, so there is a con also. So if the pre-pages are unused, then the IO and the memory are wasted. So so assume there are ace pages are pre-paged. A fraction alpha of these ace pages is actually used. So alpha between 0 and 1. So is the cost of uh, ace into alpha. So ace into alpha, say pages greater than or less than the cost of pre-paging ace into 1 minus 1 alpha unnecessary pages. So these are very valid question. Is the cost of 1 minute? Am I audible now? Can you confirm? Am I audible now? Yes, sorry. So there was some problem with the microphone. Yeah, sorry. So I will repeat it again. Okay, sorry. Uh, oh, let me do it again. Yeah. So I was discussing that. So why do you need pre-paging? So last week we came across this term called thrashing, right? So what was happening in thrashing? So there was continuous movement of evicting a page from your main memory and loading another page after each, let's say, after each process requests one and all. So what we saw in thrashing was that our process was spending considerable amount of time in in evicting and bringing one page back and forth. So that was a big problem. So one thing that can be done to stop that thrashing and all, to solve that thrashing and all, is pre-paging. So pre-paging is used to reduce the large number of page faults that occurs at process startup. So what you can do is pre-page all or some of the pages a process need before they are referenced. So if the pages are, so one problem is that when you are pre-paging a lot of number of pages, what happens is that a lot of IO and memory are wasted because all of the pages may not be required at the time, right? So your memory is limited, and you are doing is you are practically bringing a lot of pages from your secondary memory to your main memory, but you're not able to you're not going to use it for some reason. So a big question arises here. So suppose there are ace pages are pre-paged, so ace pages are prepared, alpha fraction of them of these ace pages are actually used. Question is the cost of is into alpha saved pages false greater or less than the cost of prepaging s into 1 minus alpha prepages. So that means there are s pages that have been pre-paged, so they are in the memory, so out of which they are saying alpha, uh, out of which we are saying is alpha have been used. So alpha, so the question is S into alpha is the total number of pages that have been used. So by pre-paging we are saving this amount of page faults, right? So is this the cost of this is less is greater or less than that of this S into 1 minus alpha, that is pre-paging these wasteful pages. So this is one of the big criteria behind whether you want. Uh, what is the optimal number of pre-paging that you need? That's the question here. So that's the big context here. So there are other issues also. So this is one issue, that pre-paging. So another issue is page size. So basically, uh, so another issue is page size. So page size is basically the size of the page. So one option can be a page can be 4 KB, or a page can be, let's say, 16 KB. So which one will you use? That's a big question. So like, you are given two options, right? So it depends. page for size selection, you need to take into consideration many things like fragmentation, page table size, resolution, IO overhead, number of page faults that have to be sufficient, locality, and TLP size and effectiveness. So these all things you need to consider. And why you need that? Why you need to consider that? Suppose fragmentation. Let's say consider the case of fragmentation. If you are using a smaller page size, will there be less fragmentation or more fragmentation? So what is the reason for fragmentation? So basically, what we need to know about that is basically you have frames, and there you need to store the page, right? So if you have frames, let's say of size 8, let's say of size 20 KB. So if you have a page size of 4, so only a small portion will be used and the rest will be free, right? So that will create fragmentation. Whereas if you are using a page of size for 16 KB, you are complementing a lot of portion of the frame, so the fragmentation will be less. So those kind of considerations you need to make. So what will be the optimal page size? You need to take into consideration this, like what is the frame size that is there, so that will be less frame size. So along with that, I over it, like I over it, it is very simple, right? So the amount of time you require to transfer a 4 KB page, right? So just say, think about it. So amount of time required to transfer a 4 KB page is obviously less than transferring a 16 KB page, because it is more size, so it will always take more time. So these are the practical considerations you need to take. So on arriving at what optimal page is required for your job or program, always will be power of 2. That is uncompromisable thing, because it helps in faster calculations. So if you are doing it in the power of 10, calculation will be little jumbled up. So it is always best to do this kind of calculation in power of 10. On average, this page size always increases. uh, Next is TLB reach. So what is TLB? So we have previously discussed. TLB is basically a sort of faster memory to hold pages. It's sort of a faster memory to hold pages. It's sort of a cache, you can say. So TLB reach is basically the amount of memory accessible from the TLB. So TLB reach is basically what is the TLB size and into the page size. So there are, let's say a TLB has 4 columns. Let's say I have 16 columns, and the page size is 4 KB. So what will be the TLB reach in that case? TLB reach in that case will be 16 into 4 is equal to 64 KB, right? So that is your TLB reach, the amount of memory accessible from the TLB. So in ideally the word set of each process is stored in the TLB. Otherwise, there is a high degree of page faults. So most of the cases, the like as you know, so like TLB stores basically the concept of TLB comes from the locality of references, right? Where TLB tries to store which is the next page that will be required by the process, trying to guess it. So, so what happens if you increase the page size? So this may lead to an increase in fragmentation, as not all application requires a large page size. Further, the working providing multiple page sizes. This allows applications require larger page size than opportunity to use them without a fragmentation. Okay, so TLB has its own set of values. So if you increase the page size, it will result in fragmentation. So let's say if you have if you have prepared a page size for 16, the TLB, and now you are using four, only four of it. So you have prepared it for a 16 KB size. Now you are like you have prepared it for 4 KB size. Assume that, and now you started using pages of size 1 KB. So you will be filling out this much, and this big gap will be left to will be left out. So that is the again the problem. So if you are using high page size, so you are creating fragmentation. But also notice, so TLB is costly, right? So TLB is costly. So fragmentation for TLB is bad news. It's bad. It's basically bad. If it gives rise to fragmentation, it is basically bad. So next, this is a very interesting one. So program structure, how the program structure and the size of the and how you are arranging your page have a close effect. So this thing can also be not only be generalized for page, but this thing can also be generalized for cache. So cache is not there, but let's try it for pages. So how program structure defines how your program will run. So you think about it like this. So you have a array of size 128, 128, 128 rows and 128 columns. Suppose each row is stored in one page. So what we are saying is this row uh, in page 1, page 2, page 3, and last one is stored in page 128. And suppose you are so this, what does this code do? This code is basically initializing the entire array with 0, right? So we are basically uh, initializing the entire array to 0, right? So how we are doing it here? So if you look at this code, data, we are doing data ij. So what does this mean? So how you are accessing this one? So how will this code run? So first it will initialize data 0, 0 to 0. Then we will do data. Let me just read over it. So first we will do data 0, comma 0 to 0. Then what we will do? So we are increasing the I value. So data 1, comma 0 to 0, data 2, comma 0 to 0, and then what we will do? D 127, comma 0 to 0. Then we will do D 0, comma 1 to 0. So how are we accessing this? We are basically uh, how we are doing this? So basically we are picking up this entire column. Yeah, so basically we are picking up this entire column and filling up with zeros, right? But we know, so we are, yeah, so that we have done here. Yeah. So now what is the problem? Uh, so now the problem is, while the each page is stored in our this wise, we are basically accessing the data row wise. So each row first data we are completely. So column wise we are analyzing it to zero. So now what happens here? So let's say initially the page, the program has only loaded one page. So let's say it has initially loaded page one, right? So page one you have data 0 comma 0 to data 0 comma 127 stored in page one, right? So initially you come with the program sees that okay, I have to initialize data 00 to 0. So it basically uses the page one to do it. But next what happens? Next it requires data 1 comma 0. Now data 1 comma 0 is not present in page 1. So what it is to do, it evict page 1 and bring page 2. Right. So that it needs to do. So there is a problem. So there will be for initializing this entire column, you will have 128 page faults, right? Similarly, for covering the entire array with 0, you will require 128 cross 128 is equal to 16384 page faults, right? That is the problem. While each row is stored in your in one page, but you are trying to initialize each column at a time. So there lies the problem. But now let's consider this program 2. What does this program 2 does? So what does this program 2 does? So this program 2 accesses it in this format. Same format you can see, but outer loop is I and inner loop is J. So data will be filled like this: data 0 comma 0, data 0 comma 1, data 0 comma 2 dot dot dot, data 0 comma 127, then it will go to the data 1 comma 0. So as a result it is now filling up the entire row at a time. So it is filling up the entire row at a time. So initially when there is page 1, so there will be only one fault when you move from first row to second row. So the number of page faults in this case will be only 128, because to cover each row the entire column is present there, entire row is present in the page one and you are doing it in row wise. So that's the advantage you get when you are dealing with a better program structure. So in the first case when there are large number of page faults and it will be slow, in the second case it is basically faster because it has less number of page faults. So this kind of array manipulation is very common when you are writing a C code, but you never thought about it, which one is optimal and not. So now you will get it like, okay, this one is better because it will require less page faults to deliver the output. So any doubt regarding this you can ask. Okay, so let's go to the next one. So now what you have is this IO interlock. So page must sometimes be logged into the memory. Why? Because consider the IO pages that are used for copying a file from a device that may be locked from being selected from eviction by the page replacement. So you have a device. So suppose you have a USB device. and you want to copy the entire into the main memory, entire disk to the main memory. So there is this. So the page involved for the process should not be should not be evicted out because it will hamper the transfer, right? So that's why you need that process to remain in that page to remain in your main memory. So what you can do is you can lock the memory. So what you need as this IO interlock to lock the memory so that it does not get evicted from your main memory, and it completes the transfer of this data from USB to memory directly. So that is why you require this IO interlock. So with that, you end the virtual memory concept. So I will say this one is very quite this part is very important. This program structure. So you may be given a code like this, and you may be asked that uh, like how many faults will be there for this amount of code. So this is very common question that is asked in many exams and all. So this one you need to remember a little how to do this kind of stuff. So any doubt you can ask. Okay, so let's go to the next one, next topic. So we come to the last one, the file system and memory. So far what we have dealt with. So if you recap total in the OS class. So we started with process, right? So so we started with process. We went through process OS scheduling of processes. We also went to various kinds of problems of CPU, of uh, mm, what we call that, uh, deadlock, right? We went through this kind of topics and all. So after that, we went to memory part. So while there was initially only CPU based stuff we dealt with, we went to main memory and virtual memory. Now we come to the topic of secondary memory, like how OS interacts with your secondary memory. So what is basically your secondary memory? So anything that is stored in your files. So secondary memory is basically, while main memory is your RAM and all. Secondary memory is basically the memory where you store your files, so that it doesn't get erased, or it remains in the memory irrespective of when you shut down the machine and restart it. So it remains there. So it is a non-volatile memory. So we now will deal how OS interacts with this SM, this secondary memory. So, so have a look at this diagram. So these hierarchy have been available to you for for quite a lot of amount of time now. So as you can see, uh, so on the top you have your registers. That is the fastest memory access as well as the smallest. The reason for being small is basically it's costly. Then you have so these are the registers are basically stored in the CPU only. Those are the fastest form of memory. Then you have your cache memory. Then you have your main memory. So these are all your primary storage, and they are volatile. So volatile means it gets erased when shut down. Right. So that is your volatile memory, and then your comes to non-volatile memory. So in non-volatile memory, you have your magnetic disk, optical disk, and magnetic disk. So as you know, these are your basically your secondary storage. So this memory remains whenever you even if you are not using your machine. This get this whatever you stored in these disks and magnetic or optical, so they remains there. So, and these are very slow, as well as these are slow, as well as these are very large in size. So, your typically your hard disk, that is your HHD hard disk, is basically around, you can buy around 1 TB of hard disk, which is very normal these days. So also you have your SSDs, though they are a little bit costly, but still people use like say 256 GB of SSD. So people use that amount of SSD and all. So these are your this is your basically your hierarchy of how your file system has. So now let's come to this how your how basically is data stored in your magnetic disk and how it happens. So let's draw some diagrams. Just wait a minute. Yes, for some reason I'm not able to admit someone. Yeah, Abhishek, you can ask. So if you have any doubt, you can ask. Yeah, so let me start this one. Yeah, so let's come to you how your disk how your disk is organized. So let's say this is one. Uh, this is how your disk looks. Let's say. So there is a column of these disks. So let's think about it like this way. So there is this disks. Okay, so a column of disk. So so each one of these, this is one disk, this is one disk. So each one of these disk is called a, what is this called? A track. So each one of this is called a basically a plate. Sorry. So this is called a plate, right? So if we go a microscopic way of how this plate look like, so let's draw it again. So this is a plate. So in this plate there are many small. These are very small areas. What type of question is asked in exam? So in your exam, basically the questions that are asked are similar to uh, how your assignment questions are there. It will not be very difficult. It will be similar to how what we have done in the class and how it has been uh, given in your assignments. It's quite similar to that. Okay, so let me complete this. We will come to the exam eventually. So you have your plate, and inside the plates there are many circular regions. So each of these circular regions, this one, this one, this one, and this one, are called tracks, right? So each of these circular designs are called tracks. So this one is one track, this one is another track, this one is another track, and this one is another track. Now each track has further been divided into another part. So suppose this is one track. So this one is a circular track. So this one is your track, let's say. So inside this track is further a small portion. This one is called your sector. So a sector is basically your like the minimal like the unit of data that is stored, unit place where the data is stored. So this is the unit place where your data is stored. Right. So now the question will be, how are you going to access the data? So when you have data like this, where the data has been stored in such disks, and where each disk has something called plate, a track, and each track has a sector. So the question is, where sector is the one that has been storing the data. So how are you going to access the sector? So what you have is something called a needle. So So this column has something called a needle. So what does this needle does? Suppose a request come to access a, let's say there is a sector here. So there is a sector here. So the access this data. So a question comes that a request comes to you need to access this data, and let's say the needle at this point is pointing here. Let's say the needle at this point is pointing here. So what it needs to do to go here? So basically it moves the needle. So it basically moves the needle from here to first this plate. Now inside the plates it searches in which track this sector is. So it comes to this sector. So here is the so the needle comes to here, and okay, this is a sector where I need to store or get the data from, and then it comes to the sector from where the request from IO or has come or not. So that is how your data operations happens. So you have your circular disks. So which is basically your called a plate. Inside a plate you have your tracks. So you find your track and then you find your sector from where the data has to be moved in and out, and that is how your entire operation of IO happens. So once you find your sector from where you need to transfer or data, so after that direct transfer happens. So that is basically what is shown here. So you have your plates, you have your plates, and then each plate has a sector, and each plate has a track. Sorry, each plate has a track. So this is number one. This is number two. Each plate has a sector, track, and each track has a sector. So if we come chronologically, so you have a plate, then you have a track, and then you have a sector. So that is how is the data is organized. Okay, so any doubt regarding this cylinder structure and all, you can ask. Okay, so let's come back. So you have no doubt. So let's go back to the next part. So uh, let's now devise how you are transferring the data. Okay. So first is your seek time. So average access time is basically let's say let me just first write the equation. So access time is equal to seek time plus rotational latency plus transfer time plus uh, let's say controller time. So this is basically not considered many times, but these are basically extra stuff that happens. So let's first think about each one of them. So let me number this as number one, number two, and number three. So number one, seek time. So so seek time is basically you need to moving. So basically it is time required to move the needle to particular track. Okay, so this is your track. So this is your track. So the time required to move from here to here in this track. So that is your seek time. Number two is your rotational latency. So what is basically a rotational latency? Rotational latency is moving. So from so you are so suppose after moving you are currently in this sector. Let's say currently you are in this sector. So you need to reach this sector to transfer the uh, to do the IO transfer. So you need to move from here to here. So that is basically a rotational delay. So rotational delay is time to move to target. So what this particular track, let me use the term target track. Time to move to the target. Uh, time to move to target uh, sector. So that is your rotational delay. Third is your transfer time. So once you have reached to the sector, so now you will what you will do, you need to transfer the data, right? So once you have reached this sector, you need to transfer the data. So that is your basically your transfer delay. So how much time is required to transfer the data, right? So that is your basically transfer delay. So time to read slash write the sector, that is your transfer time. And last, this is your controller time. That is some miscellaneous stuff that you require to move this controller to particular place and all. So it basically comes into how much time you require in an IO buffer or stuff. Let's say how much time you need to respond to these requests. So like you are requesting a IO operation. So basically it will require some delay and all because of those application level stuff. So that is your extra stuff that controller delay is. So that is how you calculate your access time. So basically there are four parts. So one is your seek time, one is your rotational latency, one is your transfer time, another is your controller time. So in exams, they give you to calculate this access time, which is a very common question. Generally, the seek time. We will solve a problem related to it today. So in most cases, what you have been given is your seek time, then you have your rotational latency, then you have your transfer time, and you calculate all of them and then add it. So any doubt regarding this formula and all, you can ask. So this is a very important topic. Should ask questions. Okay, so let's move on. We will solving some problems related to this later. Yeah, so these are some things and all. So these are the things we discussed now. These access time and all, average seek time and average latency, basically rotation latency. Average IO time is basically your average access time plus amount to transfer the data, transfer it, which we discussed now, and the controller overhead. Now let's have a look at the disk structure. So disk drives are basically a large one-dimensional array of logic blocks, where logic block is the smallest unit of transfer. So a one-dimensional array of logic blocks is maintained into a sector of disk. So sector 0 is the first sector, sector 0 is the first sector, and then there is a lot. So think about this way. So this is your sector. So this is your track, right? So track is divided into multiple sectors. So what is this? So this is basically a large one-dimensional array, right? This is basically a large one-dimensional array of space, and they are mapped into a sector of so this is your, let's say, sector 0. This is sector 1, 2, 3, 4, and all. So mapping is proceeds in order through the track, then the rest of the track and all. So logical to physical mapping should be easy, except for back sectors. There can be sectors that are bad, that are not being used, and there is a non-constant number for each sector. Uh, each sector basically are 4 kb, the smallest unit. So this size of it is basically 4 kb. So nothing much important. So you have your sector. So they are basically a logical array kind of stuff that you think about. So now let's come to the problem of disk scheduling. So far we have seen these stuffs, right? So we have seen this kind of scheduling algorithms. Like you have seen the CPU scheduling algorithms. So basically process scheduling. So which process to go and all. That is one thing you have seen. You have also seen page fault. That kind of scheduling, like which one to evict and all. So now what do you mean by disk scheduling? So what do you mean by basically disk scheduling? So disk scheduling is a term referred to something like this. So you have, let's say, you have this nice beautiful track, right? So you are currently in this sector. Okay. Now you are, let's say, this sector is 180 sector number. Now let's say here is your sector number 45. So next a request come, or a IO request comes for sector 45, right? Next sector request come in the at the same time, let's say 1 or 2 seconds while you are serving this IO. So let's say from 97. So another, let's say, comes from 212. So sector. So once it finishes this part, it sees that it has the OS says that it has these three IO requests has arrived. So the question that will be asked is, which of these disk schedule should be scheduled? Like which of these sectors to be next tried out? Question is, which of these should be should be addressed. So which of these schedules should be addressed next? So that is one which will be the grasp of this problem. So logically, one solution you may think is, okay. So 45 has arrived first, so let's sub 45 first. Then we will arrive at 97 and 2100. But you need to think about it. So this is basically a needle, and that needle basically moving on the sectors. Uh, so, uh, think about it like this way. So in the movies and all, you have seen this thing called gramophone, right? So in gramophone, you put a pin on the gramophone. So nobody now uses gramophone, but if you have watched some films and all, so you will see that this thing called gramophone. So what does you do in a gramophone? You put the pin and do it on the put it on the gramophone, and basically the pin moves around the gramophone and it plays the song. So this concept is quite similar to that. Now the question is, so you have to move from 180 to 45. Won't it be better if you start 112 first, right? Because in that case, the pin doesn't have to move a lot at, at the beginning, and it will be served faster. So that could be another logic, that a greedy logic, the one that has which is very nearer to my needle, I will move that side. So that is a very greedy logic, and that is also supported in most cases. So we will come one by one to all the disk scheduling algorithm, and we will also saw what are the pros and the cons of each of them, right? So let's go back to them one by one. So suppose you have this. So this is your schedule, like requests, IO requests, and currently the pointer is at 53. Okay, so currently it is serving 53, and it has this list of requests available into it. So we will first look at this FCFS. What is FCFS? First come, first serve. So initially it is at 56. So initially it is at 56, right? So this is it is initially. So next it will go to 98. So it comes to 98. Then it goes to 183. Then it goes to 37. Then it goes to 128, 122. Then it goes to 14. Then it goes to 124. Then it goes to 65, and then 67. So this is how your FCFS serves the requests, right? So very simple. The one which comes first, the needle moves to that, and then the next one, and on. So if you calculate what is the total head movement, so how much the head moves in this case. So pretty simple. What you will do is you calculate the distance between this, then the distance between this, then the distance between, then the distance between this, then the distance between this, this, and this. So if you calculate it, it will come down to 640. So the needle has to move around 640 times. Okay, so FCFS is not ideal. Okay, we'll look at the other ones next. You will see that those are much more optimal in the sense. So next we come to shortest seek time first. So as again you have the same queue, and the head is currently at 53. So what will shortest seek time first do? It will go to the one that is nearest. Okay. So what is nearest to 53? So nearest to 53, the candidates are 37 and 65. Right. So, 53 to 65 is basically 12. So it basically will go from 53 to 65, which is the closest. Then it will go to 65 to 67 because it is the closest. Then what is the closest to 67? Is it 98 or 37? So it is 30 in this case, and this case it is 31. So 37 is the closest. So it goes to 37. Now from 37, the closest is at 14. So it goes to 14. Now from 14, the closest is 98. It goes to 98. Then it goes to 122, 124, and lastly 183. Right. So if you now count the total head the total head movement is basically this, right? So if you count it, it will come down to 236. So what we found is SSTF, that is shortest seek time first, is better. It takes less time, much less head movement than FCFS, right? So in a way, that is it is much optimal way of scheduling the requests. So any doubt regarding FCFS and SSTF? Okay, so now we will look some advanced features because the problem with STFS is like any other form of scheduling, it may cause starvation, right? So if at any seconds, so if it founds like even if let's say 98 is is announced much better, much ahead, but you see this one 67, 65, 14, 37, which are announced much later, are basically getting served fast than that. Even 183, look at 183 is served. After serving all of them, 183 is served. So basically like any other greedy scheduling algorithm, like all greedy scheduling algorithms deals with the same problem of starvation. So that is the main issue with STF. So we will come to much advanced solution than this. So here we come to scan algorithm. What is scan algorithm? So what the disk in this case does, the disk can start at one end. So it starts at one end. So let's say this is your disk. What it does, and let's say you divide it like this. So 0 to, let's say, 200. So what it does is, let's say it is now at 53. So what it does is it goes from this to this and serves whatever request that has been present. After that, what it does, it reverses the path and it goes from this to this, and then it again reverses from this to this, and it continues. So whatever request is present while it is on this path, it serves. Whatever request is present in this path, it serves. Whatever request is present in this path, it serves. Okay. So we will go through the example, and what we will find, it requires much less movements of the head. Let's say here. So head starts at, let's say, 53. So 53, it goes to 37, then it goes to 14, then it goes to 0, and from there it shifts the uh, channel. So um, one more thing I will say is that there is no hard and fast rule that it has to go from this to this. It can also go this direction and come back. So that is not a big issue. So it can go in this direction also, and initially it can go this direction also. So that is not a big problem. So if you look at this, if you calculate everything in the total head movement in this case, where it goes from one end to another and then serves the other into another other request, it will come down to this 208 movements. So total movement in this case will be 208. So you can easily calculate how this 208 comes. So it goes from 53 to 0. So that is 53 plus this to 128. So 183. Mm, sorry, it starts from this 37. So it starts from this and it goes to this. So total will be the total distance from here to here. So I guess it is given wrong. So it will be like this. So 53 to 0, that is 53, plus 0 to 183. 183, that comes down to 236. So that will be the yeah, this one is given a little wrong. Okay, so still if you see that it is much less than the previous one. So now let's wait for another. Let's look at another type of scan solution, that is called C scan. What C scan does is it always makes the one side of movement. So it treats the cylinder as a circular list. So it goes from 0 to 200, and then it again starts from 0 to 200, right? So the scan is always in one direction, and it comes from this very notion that the discs are circular. So if you this consider this is your track and these are your list. So let's say it starts from here. So let's say this is the zeroth list. So if you go back here, so suppose this is a 200. So after 200, it will be zero only. So it continues like that. So it treats a cylinder as a circular list. So and which is more practical if you think about it. So it does like this. It 53 to 65 and all. So it comes to 199, and then it again reverses back into this. Right. So that is what it's doing. So it's going from this to this, and then again it reverses it from this. So in real life, you don't have to consider this movement, because the list from 0 to 200 to 0 is basically zero movement, because it is a circular list. So you don't have to add that up. Maybe I did the same mistake here. Okay, so now we will look at this one. It's called look and see look. So look is a version of scan. Okay, so the arm only goes as far as the last request in each direction. So what was happening here? What we were doing is we were moving to 0 to 200, and then coming back to 200 and then going. So we doesn't move up to the end. We serve only up to the last request. That is, if it is 183 is the last request, we then move back from that. Okay. So that is the main difference. And C-look is similar to C-scan. So instead of starting from after reaching this to start from 0 again. So instead of starting going to 200, it starts from 0 again, and it doesn't go back to 200. It stops at 183. So that is what is being done here. So this is your C-look. So it starts after this and this, and then it starts from 14. C-look is similar to that. Look and see. So these are some points that you need to remember. So SSTF is common and a very natural appeal, but it starts from it has a problem of starvation. Scan and C-scan perform better for systems that are heavy loaded on disk, so less starvation. So there is a heavy load, scan and C-scan are better. Performance depends on the number of types and requests. That is a big thing. And the request for device service can be influenced by the file allocation method. So that is also being thought about. Next, let's discuss in little details this reliability and redundancy. So time to failure is basically average time it requires to for a disk to fail. Then mean time to repair, the time it requires to repair. Then there is mirroring. Mirroring is basically you have one disk, so you want to mirror it to another disk, the content. So that is what is called mirroring. So copy from D1 to D2. That is one thing. Okay, and to do redundancy, so to save us from failure, what it does is what is a very common example is redundancy. So what is redundancy? Is basically you are doing these interloved things. So you have four disks. What you do is you mirror the four, or you do parity checking, parity based error correction that you do. So these are your main disk and this is your parity disk. So these are all the types of like redundancy check you do mostly. Okay. So with that we come to the end of this. So we'll be next discussing some problems related to this topic which we discussed, this disk scheduling and all. So if you have any doubt, you can ask. Okay, so let's do some problems, solve some problems related to this week. Okay, so let's look at this problem. So you have the disk has 300 cylinders, and the initially it is at the wire head is at 101. So wire head is at 101. Calculate the total movement for the head request for this SSTF policy. So you have this SSTF policy. You need to calculate what is the total head movement. Okay, so initially it is at 101. So from 101 where it will go. So let's think about this way. So which is the closest number to 101? Is it 123? Is it 845? Is it 87 and all? Okay. So if you calculate it, the closest from 123 is 101 is 87. Closest is 87 because the difference in this case is 14. Whereas if you consider 101 to 123, the difference was 22. Right. So this one is the closest. Then which one? After so 87 is done. So the closest to 87, one candidate is 123, another candidate is 45. So this is 32 if you minus it, and this is How much? 36. Right. So the closest is 45. Right. So we will choose 45 next. That is a difference of, oh sorry, I made a calculation mistake. Sorry. It is 87. So 45, 87 minus 45 is basically 42. Right, 42, and it is basically 36. So 87 to 123 is the closest. So it will be 36. Now which one is closest to 123? Uh, is it 198? So is it 198? Is it 198 or is it 45? So 123 to 198 is basically 75, right? 123 to 198 is 75, and here it is 78. 78 plus 45 is 78 plus 45 is 1. Yes. So we will choose 198 because it is the closest. Sorry, 197. Sorry, I make a mistake. 197 is there. Yeah. So we are doing is 197. That is 74, and then the closest is 198. 1. So we are done with 123, 87, 197, 197, 198, and all. Next we have is the closest is 250. Obviously 250 is the closest, that is 52. Then the closest is 280, that is 30. And then the closest is 45, that is 1, that is 235. So if you add this one up is 50, this is 50, 124, 125, 177, 307, 207, 207, 235 is basically 442. So if you add this up, it will come down to 442. Okay, so what we are adding up is 14 plus 36 plus 74 plus 1 plus 52 plus 30 plus 235. So what we are adding up basically is the this stuff, the difference. So the shortest task first, shortest seek time first will give us a total of 442. That is the correct answer. So any doubt regarding this you can ask. It is little bit complicated, but it is very easy to do. Just need to remember the concept of SSTF. So let's go to the next one. So now we have a C look. So we have a C look one, and we have the same request, and the head is currently at 101, and it is moving towards the higher end of the disk. Okay, so it is moving from 101 to the higher end of the disk. So it will be 101. Next, 123. Sorry, 123. Next, it will be how much? What will be the next? Next will be 123 done, 101 done. So next will be 197. 197. So it is going up. 197 done. 198. Next it will be 280, 250, and 280. Right. So it will move up and then it will come down. So it will then move 45 to 87. Right. So what is the total movement? So this 101 to 280 is basically 179, right? So the movement is 179. Next, the movement is from 280 to 45. So that is 280 to 45 is one, that is 5, 3, 135. No, sorry, 235, right? And then there is 42. So the total will come down to the, so if you calculate it, it will be 7 and 6, 7, 9, 16, 6, 1, 7, 3, 10, 4, 5, 1, 456. So the correct answer will come down to this 456. That is the correct answer. So so what is happening in C look? You are moving from this to this and this and then this, right? So all you need to know to solve this kind of problem is you need to remember what is FCFS, what is SSTF, uh, uh, then there is shortest signal path, then they have scan, C scan, look, C look. So these are the all six algorithms which you need to remember for scheduling, and then these kind of problems are very pretty basic. Pretty basic. What you need to do is just calculate. So any doubt you can ask regarding this. Okay, so let's come back to this next question. So which of the following algorithms the disk arm starts at end of the disk and moves towards the end at one end of the disk? So which of the following algorithm the disk arm starts at one end of the disk and moves towards the end other end serving request till the other end of the disk. At the other end, the direction is reversed and the service continues. So what it is saying is this is your, let's say, 0 to 300. So this is your serving point. So it serves all the requests from here to here, and then what it does, it starts serving the request here to here. So what is this one? Is this look or scan or C scan or C loop? So it is moving from this to this instead of this. So it should be one of these, look or scan, not the circular. So it is not circular, not circular, right? So it could be either of look or scan. So what does look does? Look stops some point here where the last request is there. It doesn't go back. Whereas scan does the entire traversing from start to end. So the correct answer will be B, scan. Okay. So what happens in case of a loop? In case of a loop, it goes from 0 to 200. So this is the initial one. This goes from here to here, the last request, and then it makes the move. It doesn't go till the end of the disk. It's, it just processes up to the last disk and then reverses. So any doubt you can ask regarding this? Okay, so let's go to the next one. So the time taken for a desired sector to rotate to the disk head is called. So what it says is, so so this is your track, right? This is your track, right? This is your track. Then it says is, this is your suppose this is your currently your head, right? So the time taken to move to this sector. So this is currently in this sector. Let's say this is the target sector, right? So that is what it says. So the time required from moving from this to this. So what is that called? Is it positioning time? Is it random access time? Is it seek time? Or is it rotation latency? Rotational latency. So this is basically your rotational latency. So the time taken to reach the target sector. So that is your rotational latency. So seek time is basically finding the target track. So that is your seek time. But this is your rotational latency basically. When you are moving, when you are searching in the sector level. Okay, so let's go to the next one. of the following is not a way to make file system faster? So which of the following is not a way to make your file system faster? So put parts of the file on different tracks so that it can be accessed no matter where the disk is. Cache frequently blocks. So it is saying is that, so this is your track. So put one file in one track. So file, let's say file. So part of the file. So part of the file is stored in this track, and in another track you are putting another file, part of the file. So that is very bad way of doing it, because so from moving one track to another is basically your seek time. So in this case, your seek time will increase, right? So that is not a correct way of doing it. So this is not, will not make the file system faster. This will rather make it slow. So this is false. This is not for this is not a way of making the file system faster. So next is cache frequently used blocks in the memory. So next is using cache. So cache the frequently used blocks in there so that they can be used at faster speed. So true, this basically helps you your system faster, file system faster. Use disk scheduling algorithm to minimize the distance between the seeks. True. So use a proper disk scheduling algorithm to minimize the distance between the seeks. Put frequently used files or directories near the center of the disk on an average so that you have a far data ahead. True. So if you put it near the center of the disk, it is much faster to reach there than, let's say, some diagonal apart. So that is another way to make it faster. So which of the following is not making the system faster? That is option A. Option A is the correct answer, that it is not making the file system faster. That is much, because it increases the seek time a lot. Seek time should be reduced. So by increasing the seek time, it is making the file system basically slower than the desired. Okay, any doubt regarding this? Okay, so let's go to the next one. Oh, let me. Oh, there is a problem. Just give me a second. Yeah, so I missed this question previously. So just let do this again also. So what is the primary reason that a translation lookahead buffer is used? What is the primary reason that a translation lookahead buffer is used generally? So a TLB ensures that a process does not access the memory outside of an address space. No, that is not the correct answer. The TLB has no such functions like that. TLB makes the translating the virtual address to physical address faster, which is true, because TLB does that. That the it makes sure that virtual addresses are faster translated to physical addresses. TLB allows multiple processes to share the L1 cache. Not true. Nothing related to cache is required in TLB. TLB makes translating virtual address to physical address possible. Not true. Your page table can also do that. So, but page table is basically in your main memory, which is smaller. So that's why one uses the TLB, right? So the correct answer is option B. Uh, B is the correct answer. So now let's look at this question. For a system that performs heavy load on a disk, which of the following disk scheduling algorithm is most suited? So there is a heavy load on the disk. Which one of the most is one that is mostly used? So as you know, the answer is scan. C-scan. C-scan is basically used because in a way you go from this to end and then you go from another end to another end. Not don't need to go to another end also because this circular. You just after completing to this, you just again move from this to this and then again move from this to this and so on. So this scheduling is much more suitable for your memory related operations. Okay. So let's go to the next question. So consider the operating system capable of loading and executing a single sequential user at a time. So you have only one user at a time. So the this head scheduling algorithm used is first come first serve. Is first come first serve. So we are using first come first serve. If the first come first serve is replaced by shortest seek time first algorithm, and the vendor claims that is it has 50% better benchmark result. So what is the expected improvement in the IO performance of the user program? So what is the expected improvement in the IO performance? So notice one thing. We have how many processes here? We have utilizing only one process at a time. So process P1 is just only one process at a time it is executing. So what happens if process P1 makes a request 460? So the next request will also be come from process P1. So after this is changed, there will be only one left. Only one only left. So if the next request is from 720, it is also from process P1. There will not be much different processes because it is only one user at the time that is being executed by the CPU, by the OS. So each time the request will only come from P1 and P1 and P1 and P1 only. So whenever one request is satisfied, the next request, there will be only one request be available in the queue. And the reason is because there is only one request available, because there is only one process. So even if we replace the FCFS with SSTF, that doesn't make any sense. We rather change anything. Because the one that is available, there is only one process at the queue. Only one process at the queue. So the queue will only have one, so the buffer will be only one request. So if CFS or STFF, it doesn't matter. You chooses the one that is present in the buffer. So as a result, there will not be any improvement in the performance of the user program. It will be 0%. because basically there is no change. There is only one request at a time solved. Okay, so let's go to the next one. Yeah, this is the problem I was talking about previously. Is your average access time, how much it requires. So you have a disk that rotates at 15,000 rotation per minute. Okay, this is a very important question. This comes a lot in your exams and all. So you have a disk that rotates at 15,000 rotation per second and has a transfer rate of uh, 50 into 106 bytes per second. If the average seek time is twice the rotational delay and the controller time is 10 times the disk transfer time, the average time to read or write a 500 bits of byte of disk. So we'll come to it one by one. Let's start. So what is the total disk time that is we know? We know it is uh, total access time is basically your seek time plus rotational delay plus transfer time plus controller time. Okay. So let's first calculate the seek time. So first let's calculate the rotational time because seek time nothing is given except it is twice the rotational delay. So let's count the rotational time. So rotational time, how will calculate? So it is given 1,500 rotation per 60 minutes. That is the number of rotations that are happening. And how many rotations are made? How much will be the rotational time? This is the total. This is the total your number of rotations you are making per second, per minute. So the average rotational time will be 1 by 2 divided by 60. Because why 60? Because on an average half rotation you are making. So on an average you are making half the rotation. From here to here is half rotation. So rotational time will basically be half into 60 divided by 15000. If you calculate this, it will come down to 2 milliseconds. So this will basically this was in seconds. So if you calculate 30, 500, 1 by 500 is basically 0.002 seconds, which is 2 milliseconds. Okay, that is your rotational time. Next is your seek time. So next is your seek seek time is twice the rotational delay, that is 2 into 2 milliseconds, that is 4 ms. Okay, that is a 4 ms. Now is the transfer time, that is how much time is required to transfer 512 byte sector uh, at this rate. So it will come down to 512 bytes, and what is the speed? 50 into 106. Okay, so if you calculate this, this will come down to 10.24 microseconds. So total time is basically 4 plus 2 plus this, and the controller time is 10 times the disk transfer time. So controller time is basically 10 into this disk transfer time, so it will be 0.1 ms. So the total time will be 4 plus 2 plus 0.1, that will be 6.1 milliseconds. So 6.1 will be the correct answer. Yeah, so this is very important. So you need to find out all of the part of it. So rotational time is half divided by whatever the speed is given, because on an average you are making half rotations, and then you are making out the seek time, that is given as twice the rotational delay. Then you are calculating the transfer time. Transfer time is basically 10.24 microseconds, and disk transfer, the controller time is basically 10 times it. So you are multiplying it by 10, and it will basically come down to 4 plus 2 plus 0.1 is 6.1 seconds, milliseconds. Okay, so let's come down to the next one. So we have the following are the problems of contiguous allocation. So what are the problems of contiguous allocation? So if you are doing a contiguous allocation, so always there cannot be a free. So if you are doing a contiguous allocation like in array, so if you are trying to increase it, you will not always find a place for free file. So this is a problem. True, this is a problem. External fragmentation is also a problem. True. Compaction requirement is also a problem. So if it gives us to fragmentation, that will give us to contact. We have to compact do it. So the correct answer is all of the above. So all of the above are the problem if you are doing a contiguous allocation. Next one, match the following. File access time type is sequential or random. So what is it? So that is contiguous. So if file access time is sequential or random, that can be possible only in contiguous. So file access time is declared. File access type is declared at uh, creation. So it is contiguous or linked, and file access time is sequential but not random. So it is linked or contiguous. Okay, so the correct answer is option B. Okay, so with that we come to the end of this class or this session. So hope you have learned everything, and best of luck for your exams. So I might be taking another class on Wednesday. So if you have any doubt, you can join then. That will be a recap of all the questions which are there in this syllabus and all. So we'll solve some questions. Okay. Thank you for joining. If you have any doubt, you can ask or you can leave.